Okay, the last thing we did yesterday was we started section 4.3, and we just looked at this definition here. So again, what we have here is that the function f, that's a continuous function. It is continuous on the interval from A to B. So because f is continuous there, we know that the integral of f exists over the interval. So we know that if I look at the integral from a to x of the function f over the interval from a to x, where x is some number between a and b, I know that this integral will always exist. Okay? So what I'm doing then is I am defining a new function g, and the value of this, if I am defining a new function, right, what do I have to tell you? I have to tell you what it does to an input, right? Function, what does the function do? You give it an input, it gives you an output, right? So here, I have to define a function, I have to tell you what does the function do to an input. Well, the function g, when applied to the input x, gives you the value of the integral from a to x of the function f. Okay? That's the definition of this function. And again, at first looks a little bit strange definition of a function, but you will see that it does make sense. So for example, let's define g of x by the integral from 0 to x of the constant function 2. Okay, the value of the function g is this integral. But what you need to realize is that this function is in disguise, is really the function 2x. How? Because what's the value of this integral? Remember I said how to evaluate the integral for a constant function, right? What's the integral from a to b of c? What's the integral of the constant function c from a to b? Well, it's c times b minus a, right? So what's the integral of 2? The integral of 2 is 2 multiplied with x minus 0, right? Well, I should be a little bit more. Well, this is correct the way it is, 2x. But the next thing that I'm going to say is I have to be a little bit careful. So again, we know that this integral is 2x just because the theorem that I gave you, the integral of a constant function from a to b is c times the length b minus a, right? Now notice what's the meaning of this 2x, right? What is the meaning of this 2x? Well, if x is a positive number, right? If x is a positive number, then what is the meaning of this integral? This integral gives you the area below the graph of the function 2, right? Above the interval from 0 to x. Below the graph of the function or integrand, above the interval from 0 to x. So that's this rectangle, right? And what's the area of that rectangle? Well, the height is 2, the length is x, so the area is 2x. Right? This height here, this is y equals to 2. Is everybody okay? So g of x really telling you the area of this rectangular region. Is everybody okay? Now, I have to be a little bit careful when I look at when x is negative. So what if x is negative? So let's say I have x right here. So x is negative means the position of x is on the left side of 0, right? I'm going to use green to, maybe I should use magenta to make it distinct from the blue case. So let's say I have I have x lying here. So how does it change? How does it change how I should compute the function g? Well, still the value of g would be the same. Now my question to you is this: the value of g, will that give you this area here? Will that give you this area here? What do you think? Let me call that magenta A. What's the if x is negative, my question is, what's the value of g of x? Is that, remember, when x is positive, the value of g of x is the area right here, right? G of x is the area right here. My question is, when x is here, negative, is this still the value of g of x? Is the area still the value of g of x? Yes, no? The answer is no, not exactly, but it's actually negative of that area. Why negative? Well, notice that when x is negative, right? When x is negative, what is 2x? Negative. So it's got to give you the negative of this area. But let's see why you are getting negative. Notice that if I look at g of x, when x is negative, which one is bigger, 0 or x? My upper limit in this case is smaller than the lower limit, right? So in that case, what should I do? I should exchange the upper and lower limit, x to 0 of 2 dt. Now my lower limit is smaller than the upper limit. Now what's the value of this integral here? What's the value of that integral? It's not 2x. Remember, the value of g of x is still 2x. Okay? But what I'm saying is that in terms of area, what is that? Well, in terms of area, this is a. This is exactly a. This guy is exactly a. So what am I getting? I'm getting negative of a, right? I am getting negative of a. You realize that? So when I'm looking at the area below the graph of f, above an interval, the interval is assumed that it's going from a to b. Okay, lower limit to upper limit. Lower limit is smaller. Otherwise, it's not going to be the area. Am I making sense? So what I'm trying to say here is that, let's see. Suppose that I have the graph of a function like this, right? Here is a. Here is b. Then the area here is the integral from a to b of f of x dx, right? However, what's the meaning of the integral from b to a? Well, that would be negative of a, right? Integral from b to a would be the negative of that area. Am I making sense? The area below f of x would be the integral from a to b. A has to be smaller, b has to be bigger. But if I look at b to a, then it's a negative of that area, right? Okay, so so my point is the value of g of x is negative of the area area of the magenta region, right? And what is that equal to then? Well, this is equal to still 2x. How? Because this is negative 2 times what? Remember my formula? Integral from a to b of x of c is c times b minus a, c times the upper limit minus the lower limit. So this would be 0 minus x, right? It's always, remember, integral from a to b. So the formula that I gave you was integral from a to b of c. Right? I said this is c times b minus a. b is the upper limit, a is the lower limit. Right? So upper limit minus the lower limit. And what is that? It's still 2x, right? But however, x is negative, then 2x is negative. If x is positive, 2x is positive. Right? Is everybody okay? Here, this area is 2 times x, right? However, here, what's the area? Here, it's the negative 2 times x, right? Because area is always positive. Area is always positive. If x is negative, 2x is negative. When you take negative of that, you get positive. Maybe I'm saying a little too much, but my point is, g of x is the function 2x in disguise, right? Am I making sense? So the integral from 0 to x of 2 dt, that function is in fact the same function as 2x, right? Which is a familiar function, right? 2x. Let's look at another example. How about I define g of x as the integral from 0 to t dt? What is that integral? Once again, let me just show you when x is positive. When x is negative, you get the same value. When x is positive, okay, what's the graph of the integrand? What's the graph of the integrand function? Well, it is y is equal to t, right? What's the graph of this equation? What is the equation of y equals to x? If y is equal to x, the graph of the equation is a straight line where it makes a 45-degree angle with the positive x-axis, right? So y equals to t is just this line which is making a 45-degree angle right here. That's the graph of the integrand. So if x is here, right, what's the value of this integral? The value of this integral is the area below the graph of the integrand above the interval from 0 to x, right? Well, what is that? What's the base? What's the height? This is the graph of, remember, this is the graph of y equals to t. So what is this point here? If t is x, then y is x as well, right? So that's the point xx. You realize that? And so what's the height? Height is x as well. So what's the area? Half times x, right? Is everybody okay? This length here is x because this is the graph of that equation. So when t is on the t-axis, when t is x, y is also x because y is equal to t. So in this case, the function g of x that I'm defining as this weird looking function from 0 to x, integrating the function t from 0 to x, that function is in fact the same as half of x squared. You are okay with that? You guys are done writing it down? Should I wait? Okay, so more generally then, in general then, what's the meaning of, so remember I defined g of x to be the integral from a to x of f of t dt. In general, what does it mean? Well, assume that the function f is non-negative, right? The function f may not be non-negative, but I am assuming f is non-negative just so I can give you a nice picture of what g of x means. Okay, so if I look at the graph of f, let's say f is non-negative, then the graph would look like this. Then what's the meaning of g of x? Well, if you look at it, g of x will be the area below the integrand above the interval from a to x. So a to x, area below the integrand, that's exactly this area here. This magenta region, that's the area. So that's the value of g of x, right? If f is non-negative. Okay? But again, f doesn't have to be non-negative for me to define g of x, right? This function does not. For example, when we looked at the integral of 2, right? If I change that to -2, right? If I change my integrand to -2, how does it change my result? Well, the function would be exactly -2x instead of positive 2x, right? So same thing here. My function t is not a non-negative function, right? The function t, the graph looks like it has another part right here, right? Another part below the x-axis, right? So it doesn't have to be non-negative. So you can think about it. Okay, let's look at one more example. In this example, I am defining this function. I am defining g of x. I am defining g of x by this integral -1 up to x, -1 up to x, square root of 1 minus t squared dt. -1 up to x, square root of 1 minus t squared dt. In this case, I won't be able to give you a closed formula. Remember, for the integral from 0 to x of p dt, I said that's half of x squared. I won't be able to give you a closed formula for this in terms of x. I could if I was in Calc 2, but right now I can't. But let's see what is g of x representing. So here, what am I taking the domain of g to be? The domain of g is between -1 and 1. So what's the meaning of g in this case? Well, remember, what is the graph of root of 1 minus t squared? What's the graph of root of 1 minus t squared? Well, if you square both sides, you get y squared is this, and then it is the equation of the circle of radius 1 centered at the origin, right? But because I have positive root here, that means I get the upper half of the circle. So the graph of the integrand here is the upper half of the circle. So what am I doing? I am integrating. So what is g of x? G of x, I am integrating from -1 up to x, right? So here is -1. Let's say x is right here. Let's say x is right here. Then what is the value of g of x? So what is g of x? G of x is giving me what? The area below the circle, half circle, above the interval from -1 to x, right? The value of g of x is giving you that area, right? You guys agree with that? Is everybody okay with that? The value of g of x is that area. So let's compute one specific case. What's the value of g of 0 then? What's the value of g of 0? Yeah, g of 0 is what fraction of the entire area of the circle? 1/4 of the area of the circle, which is 1/4 of pi, because the radius is 1, right? So the value of g of 0 is pi over 4. What's the value of g of 1? What's the value of g of 1? G of 1 would be the upper half of the circle, so it's half of the circle. The area of the entire circle is what? No, the area of the entire circle in this case is pi, right? It's pi r squared. R is 1, so it's pi. So half of the circle would be half of pi. Okay, so g of 1 is a half of pi. Is everybody okay? You feel comfortable with this type of functions here? Okay. Let me now give you a more motivational example. Okay, I'm going to go back to my favorite bug problem. And let's say I have a bug moving along the straight line on the real number line, and P represents the position function of the bug, and V represents the velocity of the bug. Is everybody clear? V is the velocity of the bug. P is the position of the bug. Okay, so what is V of x then? V of x is the position of the bug. V of x is the velocity of the bug at time x. Now, I am going to assume here, in this example, I am going to assume that the motion is smooth. The motion of the bug is smooth, which means that the velocity function is a continuous function. Motion is smooth means that the velocity function is a continuous function. What does that mean? It means that the velocity cannot fluctuate all on a sudden. Okay, velocity cannot go from -1 at this moment and then very next moment it becomes 5 or something else. Am I making sense? Is that making sense? So the velocity, I'm assuming, is continuous here. Now I am defining g of x. I am defining g of x as the, let's say we are focusing on the time interval from A to B. So we are picking a time interval. Let me draw a time interval here. This is from A to B, and this represents the time interval. Okay. On the other one, on the first real number line, I am drawing the position of the bug. Okay. Then I am defining the function g of x as the integral from a to x of v of t dt. Right. I am integrating the velocity function from a to x, and that's v of t, so that's the function g of x. Can someone tell me what is the meaning of g of x? And can someone tell me what is g prime of x? In terms of the motion of the object or the bug, what's the meaning of g of x? That's what I'm asking. What quantity is g of x giving me? It's giving you the position. Your answer is almost there, but it is not quite the position. You have to make a little bit of adjustment before you could say that. Remember yesterday we talked about when you integrate the speed function, you get the total distance, right? When you integrate the velocity function, what do you get? This is not the indefinite integral of the velocity function. This is the definite integral from a to x, from time a to time x. So this value is what? If v was the speed function, it will be the total distance, right? But v is the velocity function, so what does it give me? Net displacement, right? We call that net displacement. So this is g of x. So let me say this here. At time a, let's say p of a is the position, right? At time x, let's say p of x, that's the position, right? At time x. So what's the net displacement? What is the net displacement? The net displacement is here to here, right? Isn't that the net displacement? You guys agree with that? Well, what is g of x then? Well, g of x is giving me is giving me the net displacement. And I want to go back to, okay, this is net displacement. I want to go back to, someone said it gives me the position function, and I said you're almost correct. Let's see how. G of x gives you the net displacement. So let's look at the picture of net displacement. Suppose I want to know the position at time x. Can someone tell me how can I find the position at time x? If I know the net displacement, and if I know the position at time a. Suppose I know P of A, I know the position at time A. because A is given, let's say. And I know the net displacement, that's the g of x, right? Net displacement, that's exactly g of x, right? G of x is the net displacement, right? From A to x. So given that I know g of x, given that I know p of A, what's the position function? What's the position at time x? Look at the picture. I know the net displacement g of x is the net displacement. I know p of A. How do I come up with b of x? How do I come up with p of x? What is p of x? It's very easy if you just look at it the right way. What is p of x? Remember, p of x is the distance from the origin, right? What is p of A? Distance from the origin, right? I know the distance from p of A to p of x, right? I know p of A, so what is p of x? What is p of x? I know g of x, I know p of A, what is p of x? Right? I'm asking, I know g of x, the net displacement, right? What is the net displacement? This is p of x minus p of A, right? G of x is the net displacement. This is position at time x minus the position at time A, right? What I'm asking is, what is p of x? Well, p of x is what? P of A. Actually, let me say it is g of x plus p of A, right? Am I making sense? So this is for any x between, remember, any x between A and B. This is for any x between A and B. So do I know the position function over that time interval? I know. The position function is the net displacement function, g of x, plus the position at time A. Now notice, the position at time A is what? The position at time A is a fixed number, right? It's a specific time A. So P of A is a constant right here. It's a constant. So this is a constant. So now someone give me an answer for what's the meaning of, what is g prime of x? Can you tell me what is the derivative of g? What is the derivative of g? Could you tell me that? What is the derivative of g? It should be very, very clear from the last line. What's the derivative of g? Yeah, just integrate. You just take the derivative on both sides, right? What do you get? You get p prime of x is equal to g prime of x. However, what is p prime? What's the derivative of p prime? What's the derivative of p prime? P prime, that's the rate of change of position, right? Rate of change of position is what? Almost. What's the other term? Velocity, right? Rate of change of position, that's the velocity. So what are we saying? Well, we are saying that g prime of x is exactly the velocity at time x. Notice what we are saying here in this example. Remember how we defined g of x? G of x is the integral from a to x of the velocity function dt. And what are we saying? We are saying g prime of x, is what? We are saying g prime of x is exactly v of x. Why is this important? Remember, we are defining a new function g this way, in a strange way. If I have a function, I usually want to know the derivative of that function. Why? Because it gives me the rate. Well, I know exactly how to find the derivative of g, which is what? Very simple. It's just the integrand. It's just the integrand evaluated at x, right? The amazing part of it is that this thing that I just gave you for the velocity, this bug, this thing always works. No matter what integrand I have here, if I define g in this way, the g prime of x is always the value of the integrand at x. So that's called this. If I look at the generalized version of this result, that's called the fundamental theorem of calculus part 1. Am I making sense? And that's what I'm going to write down in a second. Another thing that I want to mention here is the following. Suppose now I look at the integral from a to b of v of t dt, right? What is that equal to? Once again, you are integrating the velocity, so you get net displacement over the time interval from a to b. Isn't that exactly p of b minus p of a? One thing I want you to realize that p prime is v, right? Am I correct? Am I correct? So I want you to pay attention in these two versions here, the here and here. In the first one, it says that if I define a function g of x as the integral from a to x of a function v of t dt, forget about velocity and all the interpretations like that. This one is saying that if I integrate, then the derivative of that function is exactly the integrand evaluated at x. This one is saying is that if I am integrating, if I am taking the definite integral of a function from a to b, that's exactly the antiderivative of the integrand at b minus the antiderivative of the integrand at a. Am I making sense? In this very, very easy example, you get the two very important theorems in calculus. This is called fundamental theorem of calculus part 2. This is called the fundamental theorem of calculus part 1. If I think of v as a general function, and then those results are called these fundamental theorems. And if you what I'm trying to say here is that this fundamental theorem didn't just come up in people's head. It's just from physics and other applications, you see things like this, results like this, and you generalize that in math. And so here's let me write down the fundamental theorem of calculus now. So I'm going to call that fundamental theorem of calculus. And this I am going to write FTC1. Okay? So what it says is the following. Let f be continuous on the interval from a to b. Define a new function g of x, which is the integral from a to x of f of t dt. Okay? And here x is between a and b. So for any x between a and b, the value of the function g is given by this integral. And the conclusion of this theorem is that is the following. Then then we know that g is the function g is continuous on the interval from a to b, and we also know that the derivative of the function g is exactly f of x for x between a and b. Okay? The derivative of g is exactly the integrand f. So what does it mean? What does it mean? Well, it means that g of x is what? G of x is an antiderivative. G of x is an antiderivative of what function? G of x is the antiderivative of what function? The function f, right? On the interval from a to b. On the interval from a to b, g of x is an antiderivative of the function f. So someone remember when we were talking about the velocity and stuff about the bug, someone said the value of the integral was the position. He was almost correct. It is an antiderivative of the velocity function. However, it's not exactly the position function because you have to add that p of a, that constant. Am I making sense? Remember, there are infinitely many antiderivatives. They all differ by a constant, right? Okay. So this is what the fundamental theorem part 1 says. If I define a new function like this, which looks like a strange function at first look, but I know how to find the derivative of that function very, very easily. Okay, let me give you an example now. Is everybody done writing it down? Okay. So here's an example. If I take g of x to be the integral from 0 to x of root of 1 plus t squared dt, can someone tell me what's the derivative of g? What's the derivative of g? By FTC1, what's the derivative? Remember, FTC1 says if you define a function g as the integral from something to x of some function f dt, then the derivative is what? Yeah. Square root of is the integrand evaluated at x. Integrand evaluated at x, g prime of x. I didn't say g prime of t. G prime of x. Okay? That's exactly the integrand evaluated at x. Nothing else, okay? It's very easy. Sometimes once you know how to do this, this is the easiest derivative question I can ask on the exam. However, I see a lot of people missing this problem. I become very sad when I see that people are missing that. Is everybody okay with that? Here's another example. I am looking at the so in the previous example I had 0 to x, right? What if I have now if I define a function capital F of x, right? Instead of going from 0 to x, let's say I go from x to 0 and I take the same integrand. How does it change my function? What's the derivative now? What would be the derivative now? Can I apply the FTC1 to this integral directly? Remember when we looked at the FTC1, the upper limit has to be x. The upper limit has to be x. The lower limit has to be fixed, constant. Lower limit fixed, upper limit x. Only then you can apply FTC1. So before I apply FTC1 in this example, what should I do? I am going to rewrite this by changing the limits like this. And now I can take the derivative by using the FTC one, which says that this is negative, and the derivative of the integral function there is exactly what? The value of the integrand evaluated at x. So it's just a negative. Is everybody okay? Any questions, anybody? Any questions at all? Okay, I am going to do more examples on this next week, but let me now move on to FTC2. So FTC2, this is what you have been waiting for. This is going to allow you to compute integrals without using Riemann sums. And this is the fundamental theorem of calculus part 2, and I'm just going to call that FTC2. What does it say? It says the following: if f is continuous on the interval from a to b, and f is any anti-derivative of lowercase f, then the integral from a to b of f of x dx is the same as f of b minus f of a. Okay? So what is it telling me? It tells me that if I know an antiderivative of the integrand function, I know exactly how to compute the integral, right? But you have to know the antiderivative of the integrand. If you know the antiderivative of the integrand, then you can use this formula to come up with the value of the definite integral. Am I making sense? Now notice that this is exactly what we did. Remember, for the bug submotion, we said when I integrate from a to b of v of t, if I integrate the velocity function, I get what? Net displacement, right? So if you think of f as the velocity function, what is f of b minus f of a? Position at b minus position at a, which is the net displacement, right? You see that? So again, what this is saying is that you look at the antiderivative, evaluate the antiderivative at the upper limit, lower limit, take the difference. And that's the value of the integral. Okay? And I am going to use a notation here. Okay? What's the notation I'm going to use? Well, I'm going to denote f of b minus f of a by this notation, f of x, and I'm going to write b and a like this. So this notation means that this is helpful when you are writing down the steps to compute the integral. That you find the antiderivative, and then you evaluate the antiderivative at b, evaluate the antiderivative at a, and then you take the difference. Okay? So you will see in the next example how I use that notation. Okay? Is everybody done writing it down? Okay, now let's see how we can use it. Remember, we did this example where we looked at the integral from 0 to 1 of x squared dx. Remember, we did a very tedious work with the Riemann sums. We took the limit and we come up with the value what? Anyone remembers the value? Value of this integral was 1/3. We used Riemann sums to do that. Now, let's see. Well, can someone give me an antiderivative of x squared? What's the antiderivative of x squared? X to the third over 3, right? Antiderivative. And then, what do I have to do? By the fundamental theorem part 2, I know that what I have to do is to evaluate the antiderivative at 1. So I get 1 cubed over 3. Evaluate the antiderivative at 0. And then take the difference. And what do I get? 1/3. Right? I'm pretty sure you're saying, oh, thank God we can do this now instead of using Riemann sums, right? Well, starting from 4.3, you could just, use this to compute integrals. Is everybody okay? Now here's I really, really want you to do. I'm going to send you an updated homework, okay? And now that you know how to compute definite integrals, you should make sure that you know how to use FPC2 to compute integrals. Do the exercises that I sent you, okay? In your next exam, the final, remember almost half of it would be new stuff. Half of it would be previous stuff, okay? So it's important that you know how to integrate functions. If you don't know how to integrate functions, your final will be, let's say, it's not going to be pretty, okay? So make sure you know how to integrate.